Okay, hi everyone. This is CHEN 430 Process Design 1. And this week we'll talk about two things. First thing is unit sizing overview. Just a quick idea on how to size these units. A lot of the stuff you've covered in many of your other courses. And then we'll start talking about capital cost estimates and just how to calculate an overall capital cost estimate and operating cost estimate and other economic metrics for your project. And then this week as well, we have an Aspen tutorial covering distillation columns, and there's an assignment for next Tuesday on how to model binary mixtures using Aspen Plus. Hopefully by this stage, you're able to use McCabe field in mass transfer, and you're able to determine number of equilibrium stages, optimum feed stage, reflux ratio, all of these concepts, you've at least been introduced to them. Okay, let's move on. So this is the schedule. Again, unit size and capital cost estimates. Next week, we'll continue talking about capital cost estimates. We will also start talking about some safety aspects and then some ethics, because we need to do this as part of this course. And we will have an Aspen tutorial as well. You have one major project deliverable left, which is your process details, flow sheeting, and mass balance. Here, I need to see a flow sheet with more details than your simple base case. I need you to do a mass balance and an energy balance around every unit you're doing, and to be able to have a clearer resolution of the composition of each stream, the conditions, such as temperature, pressure, vapor fraction, all this stuff, and any additional details you want to add. Some people add, PNID. Maybe if you did an internship, you know what the PNID is. You want to add some of this instrumentation, you want to add some other elements, feel free to do so. And then the week after will be your final project presentations. More details will be provided. Ideally, I expect each group to present for 20 minutes and for the presentation to be equally divided among its members. So I want to see every one of you present. This will be done live during our scheduled class time. So please, arrange your schedules to do that. We have to do this face-to-face. And again, if you have any homeworks which you haven't submitted, any Aspen assignments which you haven't submitted, please submit all of them. All your grades will be updated very soon. I'm working on it, trying to get all your grades ready before your final project. And then one thing, I've only heard back from two groups. I need each one of you to email me a meeting time for the next 3 weeks, which is this week, next week, and then week 14, after your presentation before your final report. Just update me either one time for us to meet consistently on that time, or 3 separate times for the 3 weeks, but I need to hear back from all of the groups by tomorrow. Okay, so when talking about process economics, the most important thing to do is we need to know how big our plant is, which are the most complex units we have, which are the most complex operations, both from a kinetics perspective and from a thermodynamic perspective. And a lot of the time, this is an iterative process, and you don't get to the final really understanding of how complex your plant is until really the final design stage, or maybe just before it. And general rules of thumb for process economics, a lot of the time it's based on discussions with industrial design engineers. So a lot of the time when you're designing a plant and you want to get a gauge of how much it's going to cost, you need to look back at the literature, you need to look back at success stories of similar plants and use these as a basis. You don't want to reinvent the wheel every time you're designing a process, right? Unless you have a startup and you have a novel idea, you have a novel process, no one has done it before, sure. But most of the time, most of the process you're going to deal with, if you go in the traditional chemical engineering route as a process engineer, project engineer, whatever it is, you'll be dealing with things which have been done before. Once, maybe a million times, but there are success stories or documentation out there. You need to use these to your advantage. And technically, each major piece of equipment approximately has $1 million in capital investment. includes installation, engineering time, instrumentation, etc. And this has been a rule of thumb which has been used, for sizing plants. So if you have a plant with 3 reactors and a distillation column, you can say I need 4 million in capital investment, as just back of the hand calculation, initial estimate for your plant, and then you can obviously refine it. Might end up being 40 million, right? But as an initial budgeting thing, or you can use this as an initial estimate, and then you put your error bands. Of course, we're going to talk about this in a bit. So as you can see, your plant with a reactor and 2 distillation columns, typical price is around $3 million. And this is assuming you're not using any novel equipment, you're not using any technology which is out of the ordinary. You're just using standard technology, basic applications, or application has been done before, and you can get this. And again, this is an order of magnitude estimation, which means you could be off by an order of magnitude, or maybe a couple of orders of magnitude. That's normal. So let's start having a look at the different major equipments and how to size them and how to approach this this process. Okay. For distillation columns, you need 2 things: column diameter and column height. Okay, and height is usually easy to find because you've all learned the McCabe-Thiele method. You know that if I give you a mixture of 70% acetone, 30% ethanol, you want to separate it. You want a 95% recovery at the top. You have your TXY plot, or you can do it on a PT plot, whatever you want. You draw your top operating line, bottom operating line. You start staging off. Get the number of stages. Let's say you found the column has 30 stages, okay? And then once you have your number of stages, now you need to do 2 things. The first thing is assume an efficiency for every stage. So if you say I have 30 equilibrium stages using McCabe-Thiele, very ideal case, everything is nice. However, I'm gonna assume that each stage operates with an efficiency of 70%. And now you adjust your number of stages. So if you have 30 stages, each stage operates at an efficiency of 70%. Your new number of stages will be 30 divided by 0.7, which is 43 stages, okay? This will be the actual number of stages you're gonna use. And then in order to determine the height, you're gonna say, okay, every stage, I'm gonna say that every stage is 3 foot high, right? And this depends on the tray technology you're using. And now, we're getting into height, we're starting to look at more details of the type of technology we're using. And if you look at Perry's manual or look at other books, you're going to find all these details concerning the height of each tray, or depending on the flow rate, and you can get estimates for the height you want to use. But usually a tray height is 3 foot, 6 foot, maybe sometimes 9 foot in very unique cases. And then you say, if I have 43 stages, each stage is 3 foot high. So now you have a column which is 129 feet high, and then you can add 25% for your boiler and the condenser. Again, a general estimate, so multiplied by 1.25. So now we have a column which is 162 foot high. And now you have the height of the column, and this can be the initial estimate for you when doing the sizing, and you can use it as well to determine your costing. Okay. So this is how you get the height. What about the diameter? The diameter is slightly more complex, okay? When trying to determine the diameter, we need to think the primary parameter when thinking about diameter is pressure drop. And you might not cover pressure drop a lot during your calculations or during your course. But basically, pressure drop is the difference in pressure, how much, especially if you have a pressurized column operating at high pressure, you don't want to lose a lot of energy. However, in most cases, in the most scenarios you're going to deal with, you're going to deal with atmospheric distillation columns, because distillation columns are driven by temperature, right? They are temperature driven or thermodynamically driven or enthalpy driven processes. So a lot of the time in normal situations, they operate at normal atmospheric conditions, and you just play around with the temperature, play around with the reflux ratios to get the separation you want. And in these types of columns, you determine the diameter using equations, right? There are equations to do this. If you look at Perry's handbook, you look at any other book, there are equations to estimate the diameter or the minimum diameter. And you just plug in your numbers into these equations and use them to size your columns. So if you're using whichever book you're using for mass transfer, Cedar, or maybe you're using the book by Wankat, whatever it is, just look at the back column diameter, find the page with the equation, just plug in the equations, drill a function of flow rate, a function of density, function of this and that, and you have your diameter. And you can use this diameter and the height to determine the volume of the distillation column. And the volume of your cylinder or of your vessel is really what is used to determine the cost. So once you have the height, you have the diameter, you can assume it's a cylinder, get the volume, which is pi d squared over 4, get the cross-sectional area multiplied by the height, and then you're going to get the volume of the column. And this is really the metric you're going to use when doing the economics. Okay. And just another thing. So this, it's important to remember this, that the number of columns required. So if you want to split the distillation into a number of different distillation columns, you should not split it based on the diameter. You should split it based on the cross-sectional area. And this is sort of an advanced, I guess not advanced, but unconventional or a special case for dividing distillation columns. We're going to get into it in 440 when hopefully now you've done all your mass transfer, you've done your reactor design, you've had some time to digest all of this information, sleep on it for a month, and now we can really start making them dance, right? Splitting them based on cross-sectional area and other types of ideas out there for design. Okay, but generally for a distillation column, just to recap, distillation column, we need to look at the height, okay? Equilibrium stages, you get to your equilibrium stages, you assume an efficiency, get the actual number of stages, determine the stage height based on the technology you want to use. You want to use a sieve tray, you want to use a bubble cap tray, you want to use a ration ring packing, whatever it is. You look at Perry's, you find the typical stage height being used, multiply the stage height by the number of stages, get the overall column height, you multiply it by a factor to account for the reboiler and the condenser, 0.25, 0.4, depending on which philosophy you're using. You want to be very conservative, you want to be very, you want to be very wild with your estimates and take major risks. It's up to you, but you have to take the responsibility for the numbers you present. So usually try to be conservative with all your estimates, efficiency 0.7, 0.6, just over design it initially, and then you can zone in as you iterate, as maybe during your design stages, during your commissioning stages, you can always, not commissioning, during your detailed design stage, you can always iterate these types of calculations. And then after getting your height, we need to get the diameter. And again, diameter, we're going to use equations to do it. These are empirical equations. You'll find them in all of your books, or semi-empirical sometimes. You find them in all of your books. You plug in the parameters, usually a function of physical properties and a function of separation efficiency. You get your parameters, plug them into the equation, you get the diameter. Now you have the diameter, you have the height, you calculate the volume of this vessel as a cylinder. Once you have the volume of the cylinder, this is all you need to get the cost, which we're going to talk about in a bit. Just look it up in a chart. This is how simple initial costing of a plant is. You just need to be organized. Okay. Second major piece of equipment to usually think about when doing your initial design after distillation columns are your heat exchangers. Hopefully you covered how to design heat exchangers in your heat transfer course, but the major parameter in designing heat exchangers is your heat transfer area, right? Once you know your heat transfer area, you're 75% of the way there. If you're having a hard time determining the heat transfer area, then you won't be able to size this exchanger properly. So again, required information is usually the heat transfer area, except when you have a furnace, when you have a except when you have a furnace and when you have a fired heater, which is estimated based on the duty, right? Overall heat transfer coefficients can be found in Peter and Timmerhouse. I think I posted the book on Blackboard. If it's not there, I'm going to put it in the week 12 folder. Peter and Timmerhouse is a very good book. It has all of these tables. I'm not sure if it's still in print or if it's been out of print, but I'm going to post the book and download it and keep it in your collection. It's a very useful tool. If you should buy it if you find it out there, if it's still in print. And it's a very useful tool, especially if you become a project engineer or a process engineer, or you have an interest in working in this area. But basically, you get your overall heat transfer coefficient, you know your initial temperature, you know your final temperature, calculate your heat transfer area, and the heat transfer area really determines how big your heat exchanger is, right? Once you have this parameter, the area of heat transfer, you can get the cost of this heat exchanger by just looking at charts. And again, these charts are available in Peter and Timmerhouse. They're also available in a bunch of other books. There's a chemical engineering magazine, which every couple of months or every month downloads the chemical engineering pricing index. And you can always look up these costs based using these parameters to size your plant, okay? And they're based on economic factors, on the price of oil, price of commodities, all this stuff. So again, Q is provided by Aspen, so you can easily get the Q from Aspen, the enthalpy of heat exchange from Aspen, and this is a thermodynamic property. You can get it from thermodynamics, even if you're comfortable with this, but if you just put a heater block in Aspen, put in a feed stream, the composition, and you put in the final temperature, or you put in the final vapor fraction you want, it will calculate the Q for you. Delta T is the initial temperature, the final temperature. Usually this, you either know it in advance or you want to do some iteration to find the best process. Maybe you're doing an integration of your plant and you're playing around with the temperatures to find the best integration option. So you can, this might change. And then your overall heat transfer coefficient, you find it from books, from reference tables, and they're a function of your heat exchanger design. Number of tubes, thickness of the tube, the number of passes, the type of unit you want to use, and the material you want to use. Do you want to use a heat exchanger with carbon steel? Do you want to use a heat exchanger with stainless steel? Do you have corrosive material? You need a special type of material to build this heat exchanger. Are you operating at a very high temperature, at a very low temperature? These will all affect the design of the material, and this will affect your heat transfer coefficient, right? As well as the type of material flowing in your heat exchanger. If you have gases, very different than when you have liquids. You have heavy liquids, different than water, all of this stuff. Okay, once you have all of these parameters, you get your area, and the area is really the parameter you need to size the heat exchanger to determine the cost. So when someone asks you, well, how big this heat exchanger, he's asking about the area really. And this is what, if you're taking your fundamentals of engineering exam, or eventually taking your professional engineer's exam, this is what this means, looking for the area. Okay, let's move on. Reactors. Reactors, really, you need to get the volume of the reactor. If you're taking 422 with me, we covered this. If it's a CSTR, if it's a PFR, if it's what's the other one? Batch reactor, you have your equations for the volume, right? It depends on the type of reaction happening, depends on the kinetics. V over FA naught is equal to XA naught, all of this stuff, all the integration. If you have a PFR, you integrate. If you have a CSTR, you just plug in the numbers. If you have an ideal batch reactor, just plug in the numbers. And you have your reactor volume. And again, at this stage, even we're using models for ideal reactors. So a CSTR, the equations we used are very idealized equations. They are for an ideal unit. Whereas when it comes to actual design of a reactor, it's actually quite complex, and the actual design of a reactor will be a separate stage than the process design, right? Process design, as a process engineer, you do this. Reactor design will be maybe a separate engineer will focus only on designing the reactor, looking at the details, looking at the controls of this thing, looking at, how fast are we running our mixer, what type of mixer are we using, do we have to, have some internals to, what do you call it? Divide this reactor into chambers, compartmentalize this reactor. If you have a PFR, how are we cooling this unit? Do we have one tube or a bunch of tubes in a cooling liquid? All of these details really come into play later on. However, at the initial design stage, where you want to have a big picture design of your process, you can use these ideal reactor equations to size your reactor. However, to use them effectively, you really need kinetics. You need to have a good understanding of the chemistry, right? If you don't know the reaction that's happening, you can't size the reactor. Really, you can't just say, "Oh, I want a reactor that's going to convert carbon monoxide to carbon dioxide," but I don't really know the reaction. I have no idea how this is going to happen, and you won't be able to size the reactor. It's not going to work. Right? You need to have some kinetic details, some kinetic understanding. So, okay, I'm going to have carbon monoxide. I'm going to add oxygen. I'm going to get carbon dioxide. This is the stoichiometric equation. This is the enthalpy. And I have enough information now to size it. If you don't have this information, go look for it before sizing the reactor, because it's really that simple. And information is reactor volume with the amount of catalyst. The amount of catalyst at this stage, you make an assumption. So you assume if the reactor volume is 50 meter cubed, I'm going to say about 30% of this reactor is full of catalyst. Or maybe if you have a long PFR, maybe 60% of this reactor is full of catalyst. You calculate the catalyst volume, and then you can calculate the catalyst weight, and also get an estimate for the catalyst cost. But for whichever type of reactor you're using, we really need to understand the kinetics, right? Once you have the kinetic expression, you can set the conversion you want, and whichever conversion you set will determine how big a reactor you're going to need. So if I have a reaction and I want a conversion of 10% conversion, okay, very small conversion, so the volume is going to be small. You want a conversion that's 99% conversion, you're going to have a huge reactor. And then afterwards, you can do all the manipulations we talked about, in 422, where, having CSTRs in series is better than having one large CSTR. You can always do these types of manipulations where you take advantage of the kinetics, take advantage of the math, of the flow profiles to try and minimize your volume and minimize your cost. And can also be determined from residence time, as we've discussed this before. Volume of your reactor is equal to your volumetric flow rate multiplied by your residence time, right? However, to determine the residence time, most of the time, unless you have some experimental data, or unless you have some fixed value you need to use. So sometimes you want your, especially when designing a pilot plant, which is a small scale plant, you want this stuff to zip through this unit as fast as possible because you want to recycle it back, or it has to go somewhere else. Otherwise, your process is going to dry up. Then you already have your residence time fixed, and you can use this to determine your reactor volume. So, for example, if you have a solvent, in a stripping column, and you only have a small amount of solvent. It's a very expensive solvent, very small amount of solvent, and you know that this solvent can only stay in this column for 15 seconds, maybe 1 minute, and then I need it to get out and to be recycled. Otherwise, my process is going to dry out, and my distillation column is going to crash, right? So you already know the residence time. You can get the volume from there. However, for most cases, you just use your basic design equations to do that. Okay, so in pricing in Peters and Timmerhouse, remember the rule of thumb for major piece of equipment: the reactor will not cost 50,000, distillation column costs 1 million. Okay, you need to understand this. If you have pieces of equipment with comparable flow rates, their costs, your initial estimate of their costs has to be comparable, right? So if you have some feed which enters a reactor, and then after the products go into a distillation column to separate the unreacted the unreacted feed from the products, and you determine that your distillation column costs $1 million, then you cannot size your reactor to say that it costs $50,000, right? This is 20 times less. This does not make sense, and this means your calculations are off. Okay, if your calculations are always off and you're always getting $50,000, then just say, okay, it's 1 million as a conservative estimate, and you use this number in your initial design of this process. Okay, you're always better off with a very conservative estimate, i.e., overestimating the cost at the initial stage than underestimating the cost, and then when it comes to detailed design, you find out that you asked for a lot less money than what's actually needed, or you budgeted for a lot less money than what is actually needed. As opposite to over budgeting, and you say, okay, my actual design actually costs less than what I estimated. In these types of professional circles, this type of stuff looks nice, but you need to do it to cover your back. Anyways, moving on. One second. Okay, so another thing you want to consider at the early stage of design is doing a pinch analysis. Okay, and you need to do a high-level pinch analysis. And the idea of doing a pinch analysis is not to close in on the final design, but to get an understanding of potential reductions in utilities. Okay, and when doing pinch analysis, you need to consider three things: your heaters, your coolers, and reactors, i.e. your heat exchangers and your reactors, and nothing else. And usually in your base case, you don't have heat exchangers, you just have heaters and coolers, right? You're just heating and cooling using utilities. You don't have a true heat exchanger which has integration of different streams at different stages. However, once you do your pinch analysis, you can understand at what points can I include a heat exchanger at different, where I can maybe use the hot products from a reactor to heat up the feed, or I can use maybe the hot products from a reactor to heat up the reboiler in the distillation column, or I can use the hot products in a reactor to generate some steam to run a plant, or whatever it is. And these can result in significant savings in your plant, and it's actually very important to consider these types of optimization activities when designing a process. At the very first stage, at the initial stage, once you have your base case, you're starting to size all this stuff, you need to do your basic pinch analysis to get a good idea of your process thermodynamics. Because once you know where your pinch point is, you can understand at what points or at what streams can I cool and at what streams can I heat without violating thermodynamics, without violating any of these details. And a hot stream is actually two streams in Aspen. We're gonna do pinch analysis in Aspen, if not this semester, the next semester, but we will get to it slowly. I know Aspen is very clunky using it remotely, but we're gonna get there. And just think about, so you have your supply temperature, delta H, target temperatures when using a heater. However, if you want to use a heat exchanger with integration, you need to use the heat X model. Okay, what you should not include at the very first stage, don't include in your heat analysis or in your heat integration analysis, should not include distillation columns in your heat integration analysis or when determining pinch points at the very first pass. Okay, so when looking at the streams, just ignore all the streams around the distillation column and look at all the other streams. Okay, if you're comfortable, or if there's a huge energetic gradient or a huge energetic jump, you can always do it. However, distillation column design, especially in terms of temperature and pressure, tend to change significantly between the initial design and the final design. So you could have a huge temperature change, or maybe you want to take when designing this distillation column, you want to have a bypass in your column. There's a lot of different configurations for a distillation column that make it unfeasible to use it in your energetics at this very early stage. And again, due to dynamic implications, should not integrate your distillation column with the utility system, because any sort of fluctuation in your utility systems or any fluctuation in any of your stream temperatures, it might not significantly affect the reactor, right? Because if you over-design the reactor and you design it smartly enough, it will be able to accommodate such temperature changes without it negatively affecting your conversion by a lot. However, it will significantly affect your distillation column. If you look at if in your mass transfer, for example, if you increase your temperature by 4 degrees, 5 degrees, you get a huge difference in separation. If you change your composition by a few degrees without changing the feed stage location, you get a huge difference in your product streams. So distillation columns are very sensitive to temperature, unlike other columns. Heat exchanger, if your inlet stream changes by a few temperatures, your outlet stream is going to change by fluid temperatures. It's fine. Usually they can be tolerated in a process without any major issues, as long as you don't have a crossover in your temperatures, okay? But anyways, the bottom line is forget about distillation columns and flash drums when doing the initial pinch analysis of your process. Do all your evaluations in a table, try to be organized, especially when in your senior design, when you're doing the mass balance and energy balance for every unit. Have an Excel sheet, and every tab of this Excel sheet, put the name of your unit, be very organized. It's very important, because once we move on to a much larger project, when you have 40 units or 30 units, you're going to lose track of all of this. So you can't remember it off the top of your head. You need to have this tabulated in a clean way. You can always go into your Excel sheet or any other tool you want to use, and you can always see what's going on. You can always pick up on it quickly, and you can, update your calculation. And again, condenser and reboiler, you can always these are candidates, but you don't do it at the initial stage. You do it at the very end. Maybe even after commissioning and running the plant, you can do it as a second project. After the plant runs for a while, we're going to do an integration activity, project. You get subcontract, we'll start everything again as a new project to look at this integration. Once you get some data, you have some historical data, you have an understanding of the controls, all of this stuff, you can start doing all of these integrations. Okay, so this is the end of the unit sizing slides. And again, just to reiterate, we covered 3 things. First thing is your distillation columns. And first of all, your rules of thumb, okay? Order of magnitude estimate, every major piece of equipment is $1 million. For distillation columns, get your number of stages, equilibrium number of stages, assume an efficiency, get the actual number of stages, assume a tray height, or look up a tray height from one of your books, whether Perry's, Peter and Timmerhouse. These are the 2 very good books out there. Get your column height, and then you look for an equation to get the column diameter. Once you have the height and the diameter, you get the column volume or the vessel volume by assuming it's a cylinder, and you have the vessel volume, and this is the parameter we're going to use to determine the capital cost. Okay. When it comes to heat exchangers, the most important parameter is the heat transfer area, and hopefully you're comfortable with how to do this from your heat transfer course. If you forgot how to do this, go back, open your heat transfer book, and study this. If there's one thing you need to know from your heat transfer course, is how to determine the heat exchanger area. This is really extremely important for you. And really, if you know heat transfer and you know thermodynamics, you'll be able to do about 70% of the process engineering out there. So, just revise, try to refresh on these 2 things. Okay, anyway, moving on. Reactors and vessels, you use the ideal equation, whether it's a CSTR, IBR, or PFR, to get the volume of the reactor, as we discussed. However, you cannot get a volume if you don't know the reaction. If you don't know what's happening inside your vessel, you won't be able to get an estimate of the volume of the reactor, right? So if you just know that you're converting A to B and you have no clue how this is going to happen, you won't be able to design your reactor. You need to get some kinetics, you need to know some chemistry for this process. Once you know the chemistry, you get your kinetic rate expression, you can set whichever conversion you want based on your process metrics, and then you can get the reactor volume. Alternatively, in some cases, you can also determine it from the residence time. So if you know that you have a gas phase coming in pressurized and you know that's going to zip through this vessel in half a second, you already know the residence time, or you know that's flowing at a very high flow rate. So conservative estimate is 1 second. You can estimate your reactor volume this way. And this becomes important in very specific scenarios, especially when you need to control the time a certain species stays in a reactor. For example, a solvent which is expensive, or a species which is explosive, or material which poisons your catalyst, whatever it is. So you only want it to stay in your reactor for a certain amount of time. You can use this as a limiting design metric to design your reactor. And yeah, this is how you design your reactors. And then once you have your basic sizing equipment, it's always good to take a look at your initial flow sheet and do a preliminary pinch analysis. You only include the heaters, coolers, and reactors. You should not include your distillation columns and flash tanks. And this is very important to remember. At this stage, distillation columns and flash tanks are very far from being finalized. And because they are very sensitive to temperature, they are very sensitive to changes in vapor liquid fractions, we don't want to include them and account for them at this very early stage. Unlike reactors where, if you already know the conversion you want and you have an estimate of the reactor volume and you have a good understanding of the chemistry, you can get a good estimate, or a very close estimate, to the amount of enthalpy it's going to release, or the amount of enthalpy it's going to need if it's an endothermic reaction. You can use this to design or to do a preliminary pinch analysis and preliminary integration analysis. And when modeling this in Aspen, we'll cover this eventually in Aspen. This is the heater, this is the heat X model. So if you want to merge two streams, use a hot stream and a cold stream, use the heat X model. If you want to do them separately, you can use the heat model. And we already did this in one of the tutorials, if you recall. It was a tutorial about using the calculator or the optimization function. I think it was sensitivity analysis function, but we'll cover it again. Second thing is, when doing your preliminary pinch analysis, you should never account for your distillation column and flash drums. Again, processes very sensitive to temperature, so we don't want to make any promises on them at this very early stage, okay? So please try to understand what's going on here. Try to implement some of these ideas in your design project, and it's a baby design project still. Try to implement some of these ideas into it and try to get into the mind frame of thinking in this way. Okay, so now I'm gonna talk for a bit, maybe 15 minutes or so on capital cost estimate. So let me open these slides. And let me share them here. Okay. Okay, capital cost estimates. Let's introduce the idea of estimating capital costs and how does this fit into your overall design. And let's talk about these. So the outline here, we're going to talk about the components of capital costs, the types of cost estimates, estimating the cost of a whole plant, some equipment costs, estimating the equipment costs, installation costs, updating your cost estimates, and then finally, maybe some computer tools for cost estimating. Aspen has a very useful tool for cost estimation. It used to be part of the Aspen Plus package, but now it's a spin-off. It's called Aspen Economics something. It's a fancy software now, however, it's still wrong. Doesn't matter, but you can still use it to get some initial estimates. Anyways, components of capital cost. Let's talk about this. So, idea of capital cost is you want to estimate the entire amount of money or how much money an investor has to put in the project to get started. And this investor could be, could be a bank, could be a venture capital firm. If you're working for a company with deep pockets, it could be, the company itself, or it could be maybe the government, whoever it is, whoever is paying to build this plant. You need to give them an initial estimate on how much money do you need. And there are two main parameters. First parameter is called inside battery limits, plant investment, and this is the cost of the plant inside the fence. So if you think of your plant as, one big plot of land, all the equipment are inside. This includes all your equipment, bulk material, installation, costs, foundations, roads, etc. You ever been on a chemical plant? It's like a small city, right? You have all of these things happening. You have small buildings where people work. You have your installation columns. You have installation costs. You have material flowing in, material flowing out, all of the stuff. Whatever is happening inside the plant is called your inside battery limits. In contrast, you have your offsite battery limits, and this includes some external parameters, such as your site infrastructures, your boilers, your electric substations, some shipping facilities, labs, offices. If you have a research lab somewhere else off the plant, you have corporate offices somewhere which are handling this. These are called offsite or outside battery limit plant investments. And most of the time at this stage, you have no gauge of how much this is going to cost, right? So once you get your inside battery limits, you just assume that your outside battery limit or offsite battery limit is 40% of this value, okay? And this is important to be able to account for this metric when doing your capital cost, because if you only calculate your inside battery limits, you're going to underestimate your number. So again, and the sum of your inside battery limit and offsite battery limit is called your fixed capital or installed capital cost. And this is your overall cost of all the plant inside and outside the plant. And then afterwards, you have an additional cost, and then we have a bunch of other costs as well. Engineering and construction costs, how much will it cost to actually build this plant? Okay, this is not included in the inside battery cost. If you look at this, we said this includes equipment, material, installation cost, foundation, etc. However, it does not include all of the engineering costs, right? Someone has to do all the designs initially, which is, if you're working on this, who's going to pay you to make all these designs? Who's going to pay the people to, clean up the site, do all this stuff? This is an additional cost. And then you have your working capital, buy feedstock, get into business, all this stuff. These are all additional costs as well. And then you should always allow for a contingency, right? So after making all your estimates, you're going to say, okay, I'm going to add an extra 50% as a contingency in case something goes wrong, right? In case oil prices drop and it goes down to $15 a barrel, all of a sudden all of your equipment are much more expensive. You can't get equipment from other countries, and your costs are increasing, and you have a lot of cost overruns. So yeah, include contingencies to account for these unexpected circumstances, right? Or you're designing your plant, suddenly have a safety issue, something pops, and you have to stop. Government, OSHA comes to investigate. You have some cost overruns, you have delays, you have all this stuff. You account for this using your contingency funds. Okay, and this is what falls under each of these type of costs: your direct field costs, your major equipment, your bulk items, your civil work, installation, labor, and supervision. your indirect field costs, your construction, your field expenses, insurance, labor benefits, all the stuff. Your home office costs or engineering, procurement, and other services, etc. And these costs should be estimated individually. But if you don't have a good estimate, then, or if you have no idea how much they're going to cost, then you can always assume that they are somewhere between 10 to 30% of your inside battery limit estimate, okay? And most of the time, you don't really know how much it's going to cost, unless it's a project which has been done before many times and you have a lot of historical data. Then you can get a cleaner or, a better number. However, if you don't know the number, you just assume it's 10% if you want to be, if you don't want to be conservative, or 30% if you want to be very conservative of your inside battery limit investment. Okay. So the second thing is the working capital. It's the money you need to get the plant running. And all of these concepts, I'm sure you've all been introduced to it at some stage of your life, where you have your capital cost, you have your operating cost. But it's basically the working capital is how much money you need to get this plant. It's not operating costs, it's just the money you need to start up the plant, right? To buy the feedstocks, to pay bills, etc., until you start producing and you start selling your product and the plant starts generating money. Most of the time you won't be able, most of the time you don't have enough information, or you don't have a good, or you can't predict that far in the future to know how much working capital you're going to need. So usually you estimate the working capital as a proportion of your inside battery limit cost. And as you can see, we're starting to have a trend here. Most important thing is to estimate your inside battery limit. Then everything else will be an estimate percentage of it. So you need to determine your process, your measure units. As we said, every measure unit is $1 million if you want to be very conservative, or if you want to be get a very rough estimate. Every unit is $1 million for my inside battery limit. You add your contingency, you add your home office cost, say it's 30% of my inside battery limit. And then my working capital is another 15%. You see, now we're starting to get an estimate based on these, or a big estimate based on these smaller estimates. And of course, there are more sophisticated methods. If you become a cost engineer, if you become a project engineer who focuses on these costs, you can always look at extreme details. And usually in plants, we have all of these details: cash on hand, inventories held, how much product stored, all of this stuff will help us get a better idea. And then finally, you have contingency. Contingency is variation from the predicted cost. So just to account for anything that might happen, change in economic scenario, currency fluctuations, especially if you're operating outside the US, and you have a change in oil price, or you have a change in commodity prices, or labor disputes. It happens a lot in the US, where people working, they want to renegotiate things, or they want to stop working for some reason. And cost issues, weather problems, a big issue. Subcontractor problems, scope change. So let's say your plant was initially designed to make a certain polymer, but after a while you found out this polymer is toxic. We're going to change the reaction slightly and then add a separation step to make another polymer which is more workable. So you have a scope change here. You might need to redesign your plant, but you already accounted for it in your contingency cost. And rule of thumb, contingency should be at least 10% of your inside battery limit, can be up to 50% if your technology is new or if your technology is uncertain, right? So again, contingency is very important. I recommend you always overestimate contingency. If you're not familiar with the technology, if you're comfortable with what's happening and you're very comfortable with your design, then you take 10% and move on. Okay, I'm gonna stop here, and then next week we'll continue talking about the project cycle, the type of cost estimates, and other elements of the capital cost estimation. There'll be another video coming in for the Aspen Plus. Please listen to it. It's about distillation columns, how to link the McCabe-Thiele to what you see in Aspen, and how to approach these different scenarios when running your simulation. and there's a deliverable due as well. So please listen to it. And again, if you haven't sent me your meeting times, please send me your meeting times. It is very important for us to talk 2-3 times before your final report. Okay, thank you very much.